It's your teacher Daddy Courts, and I'll be looking at the concept of electrochemical cell in this video. First, what is electrochemical cell? It's a device that converts chemical energy into electrical energy. That is, it is used to generate electricity from chemical reaction. Unlike the electrolytic cell that is used to produce chemical reaction from electricity. So electrochemical cell is just the opposite. It uses chemical reaction to generate electricity. Now, you can also call it a galvanic cell. You can call it a voltaic cell. So you can call it galvanic or voltaic cell. They are all forms of electrochemical cell. Now, let's start business. When a metal is dipped into solution of its own ion, as you can see here, copper dipped into copper 2 plus, you call that half cell. This is a copper half cell, represented shortly as Cu2 plus slash Cu. This is aqueous. This is solid. You call it copper half cell. And in the case of zinc, this one is a zinc half cell. A zinc metal, can you see zinc metal that is dipped into solution of zinc ion? That is a zinc half cell. So this is a zinc half cell, Zn2 plus aqueous, right? Slash Zn solid. Now that's a zinc half cell. So when you put a metal, like we have on the screen, into a solution of its own ion, like we are looking at on the screen now, copper inside copper 2 plus solution, zinc inside zinc 2 plus solution, what happens is that a potential difference will be set up between the metal and the solution. A potential difference is like voltage, or like a kind of electricity produced. So that potential difference is known as electrode potential. Electrode potential. It happens to every metal. When you put the metal and you dip it into a solution of its own sort, a potential difference is always generated, which we call electrode potential. And if you measure it, you can see a particular value of it using voltmeter, or you can use potentiometer, anyone. You can see the value. That is the value of the electrode potential of that particular metal inside the solution. However, the value of the electrode potential varies depending on the condition of the environment. For example, concentration can affect what the value of the electrode potential will be. Temperature can affect the voltage also, that's electrode potential or potential difference. Then if gases are present, pressure of gases can also affect it. So that's why we have to generate a kind of standard condition when measuring electrode potential, so that when I tell you that the electrode potential of copper inside its own solution is, for example, 0.34 volts, what I mean is that I have done it under standard condition, which is concentration of 1 mole per dm cube, as you can see, temperature of 25 degrees Celsius, or if you like 298 Kelvin. Then if gases are present, the gases will be at 1 atmosphere. These are the standard condition for measuring electrode potential. So if you dip a metal into solution of its own ion under this condition, then that particular value you will get is called standard electrode potential, because you have gotten the voltage on standard measurement. 1 molar concentration of solution, 25 degrees Celsius of temperature, and 1 atmosphere. So take note of that. That is what we mean by electrode potential. When you dip a solution into when you dip a metal into solution of its own ion, it creates a voltage. A potential difference is created between that solution and that particular metal. And if you take the measurement as standard condition, what you will get is called a standard electrode potential. So how do we define a standard electrode potential? We define it as a potential difference that is set up between a metal and 1 molar solution of its ion at 25 degrees Celsius and 1 atmosphere. That is, the potential difference that is set up when a metal is in contact with 1 molar solution of its own ion at 25 degrees Celsius and 1 atmosphere. That is what we call standard electrode potential. Now, when you have two half cells, like we have in this place, this one is a zinc half cell, that is zinc metal put inside zinc cell, zinc solution. You also have copper metal. Look at copper metal now, deep inside copper ion solution. These are two half cells on their own. When you connect the two half cells together, you know already electricity is like there's a voltage produced in both half cells. So if you connect the two half cells together, electric current will be produced. So when you join two half cells together, that is when you have an electrochemical cell. Now what will happen when you join two half cells of a metal together? Number one, electron will flow from the half cell of a more reactive metal and flow to the half cell of the less reactive metal. As in this case, we have a zinc half cell, we also have a copper half cell. Now, from the knowledge of electrochemical series, you know that zinc is higher than copper in the series. So when you connect a zinc half cell as we have it here to a copper half cell as we have it here, then electron will flow from zinc to copper. Reason is because zinc is more reactive than copper. So you expect electron to flow from the higher metal to the lower one. It like just not very normal, very normal. In your school setting, for example, you don't expect the gate man to give money to the principal and say, principal, take money, go and enjoy yourself. That will look very absurd, but it is normal that money should flow from principal to gate man. Maybe the principal is driving out of the school and saw the gate man, and then and see the gate man maybe looking tired, so can just tell the gate man, take money, enjoy yourself. That is normal, but the opposite is unthinkable, right? So the same thing also, zinc can give electron to copper because zinc is higher than copper. Electron cannot go from copper to zinc because it be like the case of a gateman lower giving money to principal which is higher, so that cannot work. So whenever you connect two half cells together, electron will flow from the metal that is having a higher position in the electrochemical series and flow to the one having lower position. That's always the direction of the flow of electron. As you can see that the arrow is moving like this. Can you see? So as you join the two half cell through wire, it is through the wire that the electrons will begin to flow. That's through the wire. So, and what will be the direction of the electron flow? From the higher metal to the lower metal. So that higher metal, the half cell will be the anode, while the lower metal, the half cell will be the cathode. Because cathode reduction is always evolved, that is, electron is always gained, and because electron is going to the lower one, that lower metal will always be the cathode. You know that in anode, it's always oxidation reaction that occurs at the anode. Anode is a site of oxidation. So wherever electron is lost from, that is the place that is the anode. So at every point in time, the higher metal will always be the anode, while the lower metal will always be the cathode. So that in this place, zinc, where the electron is flowing from, is the anode. Then copper half cell, where the electron is flowing to, that will be the cathode. So now you are seeing that in this case, zinc will be reducing in size because the metal will be dissolving to produce electron, 2 electrons per each of the atom. So the 2 electrons will now come to this place and come and be, depositing the copper 2 ion. There's copper 2 ion in this place. So once the electron enters here, the copper 2 ion will collect the electron and become discharged as Cu metal. But here, it is the zinc rod that will dissolve and produce electrons that will flow through the wire. So I told you in school that it is the movement of electron that it creates electricity. Electricity is essentially the flow of electron. So current is produced when electrons move. So as electron is moving through this wire, current is produced, and you can use that current to do useful work. You can plug a lamp into this wire now, and the lamp will light, the bulb will light, because electron is moving through the wire. You can put a wristwatch on this wire, and then it's going to that wristwatch is going to work. In fact, I took some of my students to a competition 2020, where we are mandated to use this kind of setup to power a calculator. So, and the boy did this successfully. He power calculator by using a zinc and copper half cell like this, just by connecting the wire, these 2 wires, to the terminals of calculator. So the current is actually flowing through and can be used for doing useful work. So take note of that. I've mentioned 2 important things. When you connect 2 half cells together, electron will flow from the higher metal to the lower metal. The higher metal is the anode, that is where electron is coming from. The lower metal will be the cathode, that's where electron is going to. Now, when you connect 2 half cells together like we have in this place, an electron begins to flow through the wire. The electron will just flow maybe for 10 seconds. In fact, maybe for 1 second, and then the electron will stop flowing. The current will stop flowing. Why will the current stop flowing after maybe 1 or 2 seconds? And this is the reason. When electron is leaving here, when electron is leaving this side, electron is negatively charged. So it will leave here with plenty amount of positive charges. Like the zinc 2 plus will be plenty, while the electron are supposed to balance it will be traveling through this wire. Now, the electron that is coming here also will come and make negative ions to be plenty. Don't forget that as electron leaves here, it will leave deposit of positive ion, that's the zinc ion, will be plenty. Now as the electron gets here, it will leave deposit of negative ions, plenty. This kind of phenomenon is called charge separation. We call it charge separation, where one side is very positively charged and the other is very negatively charged. Now, Charge separation will not allow electron to continue flowing because of two different uh, charges. For this circuit to be complete, there must be neutrality across the two solutions. The solution must not be one positively charged, one negatively charged. So there must be neutrality across the two solutions. How do we achieve that neutrality? We must allow ions to be able to move from this solution to this solution. As electron is moving through the wire, we must find a technology that will allow ions to move from here to this place, so that as electron is leaving here and there's positive charge, we should be able to have a negative charge to cancel the effect of the positive charge. And as the electron is coming here and is depositing negative charge, we should be able to have a positive charge to cancel the negative charge here, so that at every point in time, no one side is more positive than the other. That is when we achieve electrical neutrality. That is when current can begin to flow without hindrance. And how do we achieve that electrical neutrality? We achieve it by using a salt bridge. A salt bridge. Can you see a salt bridge? A salt bridge is the one that connects the two solutions together and allow the flow of ions. So that salt bridge contains a salt, dissolved salt. It can be sodium chloride salt, it can be potassium chloride, it can be ammonium chloride. Usually the salt bridge contains solution of ammonium chloride or potassium chloride. So that what happens is this: there is potassium chloride inside. For example, whenever electron leaves here and deposits plenty negative charge, positive charge rather, the negative charge from the salt bridge, which is chloride, will come here and begin to cancel the positive charges. Are you getting that now? Good. And whenever the electron come to this side, the cathode side, and make that place negative, positive ion from the salt bridge will migrate and come to the solution and cancel the negative ions, so that at every point in time, here will be neutral, because as positive ion is building up, negative ion from the salt bridge will come and cancel it. And as negative ion is building up in this side, positive will come from the salt bridge and come and cancel it. So it helps to maintain electrical neutral. That's the second function of the salt bridge. Number one, it allows flow of ions, movement of ions between the two electrolytes. Number two, it creates electrical neutrality along the circuit and help us to complete the circuit. So it is when you now put the salt bridge that the electron can now begin to flow freely, because charge separation will no longer be there anymore. So this is what happens inside an electrochemical cell. So and this reaction will continue until this anode completely dissolve. So as long as the anode is still there, the lamp will still be powering, or the wristwatch will still be powering, and nothing will stop the flow of that electron. This is what we call an electrochemical cell. When you join two half cells together, current flows from the anode to the cathode. The anode is always the higher metal, the cathode is the lower metal. Take note of that. So what is happening inside the anode is oxidation. The zinc anode is dissolving to give us zinc ion. Already you know the formula for the equation for dissolving of anode. So this is what happens. Solid will turn to aqueous. That's a form of dissolving. Zinc solid turn to zinc 2 plus aqueous. That's dissolving. So the anode dissolves to produce electron, whereas the ions in the cathode accept the electron. So the Cu2 plus will get discharged at the cathode to give us Cu solid. So as you can see that in this kind of electrochemical cell, ion is only discharged at the cathode, whereas the anode go on to dissolve and produce electrons. So let us see the importance of the salt bridge, the usefulness of salt bridge. Number one, I said it allows the movement of ion. It allows movement of ions between the two half cells. Allows movement of ions. That's number one. Number two, it helps to connect both half cells and prevent the two solutions from mixing together. It helps to connect both half cell and prevent the two solutions from mixing together. Number three, it helps to maintain electrical neutrality across the circuit. And number four, if you want to add one more, it helps to complete the cycle. So you need the salt bridge. This salt bridge, you need it to complete the circuit. That salt bridge. So so the function is very very germane in electrochemical cell. So in summary, what we said is this: two half cells. The higher one will be the anode, lower one will be the cathode. Are we together? Good. Electron will flow from the anode as the anode dissolves and flow to the cathode. As you can see, the direction of the electron flow is always from the anode to the cathode at every point in time. Then ions flow through the salt bridge. Don't forget, electron flows through the wire, ion flow through the salt bridge. This is how an electrochemical cell operates. So if you don't want to use a salt bridge, you can use a porous partition or a porous disc. Can you see now? This is an example of porous disc. It can allow ions to transfer from anode to cathode and cathode to anode. It can allow ions to transfer, but will prevent mixing of the solution. This is another way you can render the electrochemical cell. Can you see now? This is the porous disc. Porous disc. So apart from your salt bridge, you can also use the porous disc. So now I want to see the difference between the electrolytic cell, the one that you already know that we have done, and then this new electrochemical cell, the one that we are doing right now. Number one difference is that electrolytic cell will convert electrical energy to chemical energy. That is, it is going to use electricity to produce chemical reaction, whereas electrochemical cell will convert chemical energy to electrical energy. That's number one. Number two, in electrolytic cell, the process is non-spontaneous. Spontaneous means the process, spontaneity or spontaneous as the case may be, means ability of a reaction to occur on its own without an external force helping it. That is spontaneous, spontaneity of a reaction. In electrolytic cell, the reaction is not spontaneous. That's why you require a battery to make the reaction work. That battery is helping, is like the external force that's making the reaction to work. So it's a non-spontaneous process. But in electrochemical cell, it is spontaneous. Once you connect the lower metal to the higher metal and you put salt bridge there, if you connect two of them through wire, current will be produced. It's a spontaneous process. Then another one is that in electrolytic cell, two electrodes are inside one electrolyte. Two electrodes are inside one compartment, one electrolyte. Whereas in galvanic cell, only one electrode is in one electrolyte. Take note of that. As you can see here, that I have only one beaker here, and it's inside that one beaker that the cathode and the anode are present. Whereas in galvanic cell, we have two beakers, right? And each electrode is in each of the beakers. That is what happens in electrochemical cell. You have two electrolytes. Each of the electrolytes contains one electrode. So finally, before we leave this topic, we want to go to continue the difference between electrolytic and electrochemical cell. That in electrolytic, salt bridge is not needed but you need salt bridge in electrochemical cell for transfer of ions. Then number 5, ions are discharged at both anode and cathode during electrochemical cell. Ions are discharged at both electrodes. Don't forget, negative ion will be discharged at the anode of electrolytic, whereas positive will be discharged at the cathode of electrolytic. But in electrochemical cell, ions are not discharged at the anode at all. The anode merely dissolve to produce electron that will pass through the wire to cathode. The only discharge of ion that occur in electrochemical cell is at the cathode. So the ions at the cathode receives electron and get discharged. Then number 6, in electrolytic cell, cathode is the negative electrode, whereas anode is a positive electrode. But for electrochemical, the cathode is positive while the anode is negative. However, cathode is still the site of reduction in both cases, so don't get it confused, while anode is still a site for oxidation. So we'll continue our class in the next video. Thank you.